We have defined the speed of light as 3.0 times 10 to the 8th meters per second. However, something to keep in mind is that it's only the speed of light when it's traveling through space. When light hits the air, or any other medium, it's going to slow down just a little bit. When light travels from one medium to another and slows down, it's going to be bent just a little bit. This is called refraction. We can relate this to a lawnmower moving from the sidewalk to the grass. The mower moves pretty quickly on the sidewalk, but then it gets to the grass. Since it is coming in at an angle, the front tire hits the grass first. The increase in friction causes the tire to slow. So now the one front tire on the grass is going slow, but the other front tire is still on the concrete, and so it's still moving at a faster speed. This causes the lawnmower to change direction. If we compare the speed of light in a vacuum to the speed of light in any given transparent medium, the ratio gives us a number that is known as the index of refraction. For example, the speed of light in vacuum we know is 3.0 times 10 to the 8th meters per second. If we measure the speed of light in water, we find that is 2.26 times 10 to the 8th meters per second. This gives us an index of refraction of 1.33. Keep in mind that the fastest light can travel is 3.0 times 10 to the 8th meters per second, so light traveling through any medium that is not a vacuum will be less than that. This means that the index of refraction of any medium will never be less than 1. And the higher the index of refraction, the slower light will travel through any given medium. In the case of light, a ray will travel through some transparent medium before running into another transparent medium, and the speed will change. The ray travels at some angle, the incidence angle, called θ1, that is measured perpendicular to the normal of the surface of the second medium. The light ray slows down and turns back towards the normal at some other angle, the refraction angle, called θ2. So light entering a new medium and slowing down, the ray will bend back towards the normal, making the refracted angle smaller than the incidence angle. Now it could be a case where the light is traveling into a medium where it will speed up. In that case, the light will bend away from the normal and the refracted angle will be greater than the incidence angle. Now the angle that the light ray is refracted depends on the change in the speed of light, and we can use a little bit of geometry to create an expression that describes this. Keep in mind that we draw light coming in as some single ray, but in reality it is traveling in a long wavefront. So some of the wavefront will reach the new medium before the rest, and as a result, that part of the wavefront gets bent before the rest. In this case, the wave is going to slow down when it enters the new medium, so we can compare how far the wave will travel before and after being refracted. The part of the wave that is in the first medium travels a certain distance. This distance depends on the initial velocity and the time period. We can say the same for the portion of the wave that is traveling through the second medium. The velocity changes but travels the same amount of time. A little bit of geometry allows us to compare these distances to each other by drawing two right triangles. For the wavefront traveling through the first medium, we can say that the sine of the incidence angle is equal to the velocity times the time divided by the hypotenuse of that triangle. In turn, we can say the same for the wavefront in the second medium, that the sine of the refraction angle is equal to the slowed velocity times the time divided by the hypotenuse. When drawn like this, the two triangles share a hypotenuse. So the ratio of the sines of the incidence and refracted angle are equal to the ratio of the two velocities. Now we also just saw that a wave's velocity changes by a factor of the index of refraction. So we get an expression that says that the index of refraction of the first medium times the sine of the incidence angle is equal to the index of refraction of the second medium times the sine of the refraction angle. This is known as Snell's law. Snell's law reinforces the idea that if the index of refraction of the second medium is greater than the index of refraction of the first medium, then the refracted angle will be less than the incident angle. And if the index of refraction of the second medium is less than the index of refraction of the first medium, then the refracted angle will be greater than the incidence angle, and the light will bend away from the normal. So we know that when light crosses the boundary between two different mediums, it will refract or bend at some angle. We also know that if the medium the light travels into has a lower index of refraction, the light will bend away from the normal. So say a light wave is traveling through water. When it reaches the boundary between water and air, the light bends at some angle according to Snell's law. According to this, if we increase the incidence angle, the angle of refraction will also increase. There comes a point where if we increase the incidence angle enough, the angle of refraction will be 90 degrees. At this point, the refracted ray will travel along the boundary between the two mediums. The incidence angle at which this occurs is called the critical angle. If the incidence angle is higher than the critical angle, the light ray will be reflected back into the water. This phenomenon is what is known as total internal reflection. Total internal reflection is the principle behind fiber optics. Basically, a bundle of thin, transparent fibers are grouped together in a cable. Waves in the form of visible light, infrared light, ultraviolet light, or microwaves, can be transmitted through the fibers via total internal reflection. Essentially, the light travels down the fiber by glancing off the surface of the fibers. Even if the cable is bent, the critical angle will not be exceeded, so the light travels down the cable with very little loss.